Hello. In this last video on complex numbers, we'll discuss complex roots and the geometry of complex numbers. First, we'll start with the following theorem that gives us the nth roots of any complex number z written in polar form. It says that the roots of z equal to r cosine theta plus I sine theta are given by rk is equal to the nth root of r times cosine theta plus 2 pi k over n plus I sine theta plus 2 pi k over n, where k goes from 0 to n minus 1. So now, to prove this, we use De Moivre's theorem. We show that rk to the n is equal to r to the 1 over n to the n times cis n times theta plus 2 pi k over n, and then we can simplify this to get this is we can simplify this to get this is equal to r cis theta plus 2 pi k. And since we're on our arguments go from 0 to 2 pi, this just equal to r cis theta, which is equal to c. So we've proved that our rk are indeed nth roots. Now we have to show that these are the only nth roots, and to show that, we note that these rk are the only nth roots of z because they are the roots of the polynomial x to the n minus z, and that has at most n distinct roots since it's an n degree polynomial. So first we calculate the magnitude of z to be the square root of -1 squared plus square root 3 squared, and this is just equal to square root 4, which is 2. So we get z is equal to 2 cis theta, where cosine theta is equal to -1/2 and sine theta is equal to root 3 over 2. Notice that these two conditions imply that theta is equal to 2 pi over 3 or 120 degrees. So from this, we write z is equal to 2 cis 2 pi over 3. Now, to find the fourth roots, you see that they are simply given by zk is equal to the fourth root of 2 times cis 2 pi over 3 plus 2 pi k over 4. And now we test this for k equal to 0, 1, 2, and 3. We can simplify this further to get this is just the fourth root of 2 times cis pi over 6 plus pi k over 2. And from this we can just plug in our values of k and find the fourth roots. Now, we turn our attention to the nth roots of 1, the real number 1, which can also be expressed as a complex number. From the previous theorem, we get that the nth roots of 1, or unity, are given by rk is equal to the cosine of 2 pi k over n plus I sine 2 pi k over n for k ranging up from 0 to n minus 1. One can observe that the nth roots all lie on the unit circle and are equally spaced due to the sequence 2 pi k over n being an arithmetic sequence. Moreover, by connecting adjacent roots on the circle, we get a regular n-gon inscribed in the unit circle. We can look at the special case of cube roots of unity, where the roots form a triangle on the complex plane that is inscribed in the unit circle. The roots are specifically 1, -1 plus root 3i over 2, and -1 minus root 3i over 2. And the third roots of unity are important because there are many results that we can prove that can help us in determining the roots of a polynomial or simplifying algebraic expressions. For example, if we let -1 plus root 3i over 2 be omega, we can see that one of the other roots of unity is just negative omega. And from this, we can see that this is actually omega squared. This can actually be verified algebraically. And we see that the sum of the cube roots of unity is actually 0 by expanding this all out. So omega squared plus omega plus 1 is equal to 0. This can be shown algebraically. So this identity involving the cube roots are not only useful when we're solving problems in complex numbers, but they can also determine the roots of a polynomial, as we will discuss in a later chapter on polynomial. So finally, we want to discuss complex numbers and their applications in geometry. So first, since any complex number z can be written as a plus bi, we naturally think to plot it on a set of coordinate axes, in which the x-axis represents the real part of z and the y-axis represents the imaginary part of z. So we can plot the point as a comma b. For example, the complex number 3 plus 4i is plotted as a point 3, 4. Now, there are some important geometric quantities we can find given 3 points in the complex plane. For example, if we have 3 points A, B, and C, we can find the angle between A and B with respect to C by first shifting down these points by C so that C is translated to the origin as so. So we have A minus C and B minus C. And this is 0. So now we can easily find the angle between A minus C and B minus C, which is just the angle between A and B, by taking the difference of their arguments. Moreover, we do the argument of A minus C minus the argument of B minus C. And by our observations on the division of complex numbers, this is just the argument of A minus C over B minus C. So in general, this is the angle between 3 complex numbers. So in particular, if C was the origin, so in that case we'll be finding the angle between two complex numbers with respect to the origin, this would just the angle between them would just be the argument of the ratio a over b. So this is quite useful, and the argument of a over b comes up quite a lot in competitions. Now, another scenario we want to consider is when we rotate a complex number z by theta degrees radian counterclockwise about some complex number omega. So in the complex plane, you have a point C and a point omega, and we want to rotate it z theta degrees counterclockwise. So we want to find this complex number. So to do this, like in the previous scenario, we shift w to the origin by subtracting w from both z from z. So we get this is somewhat equivalent to solving this problem. Then we just need to remember to translate everything back up by w, z minus w, and rotating at theta degrees. Now this is simple. If we rotated theta degrees about the origin, we still maintain the same magnitude of z minus w. We just increase the argument by theta. But according to our observations of complex number multiplication, this is just equivalent to multiplying the complex number z minus w by cis theta. So now we need to remember to scale this up, translate this up, w units. So this is our rotated complex number. Now if w was just the origin, this is just z cis theta. So this is a very useful result, as we'll see in a following example. Now we'll take a look at an application of rotation. So we imagine the following. So suppose we have a right triangle in the complex plane with vertices at w, z, and the origin, like this. And this is a right angle. So suppose that we want to find a relationship between z and w. To do this, we see that z must be some scalar of a rotation of the complex number w, and by rotating w 90 degrees, which produces the complex number w cis pi over 2, and by scaling that by some factor r, we get this relationship. Now first we compute cis pi over 2. This is just cosine pi over 2 plus I sine pi over 2, and cosine pi over 2 is 0, and sine pi over 2 is 1. So this is just equal to I. So from this, we have that z is equal to rwi. Now, taking things to the other side, this means that z over rw is equal to I. So the ratio between z and w must be purely imaginary. We can sum this up as follows. So there exists a right triangle WZ in the origin, if we have that the ratio Z over W is purely imaginary. And this comes up a lot in competitions too, so it's worthwhile remembering and knowing how we got this rotation. Finally, we'll discuss the geometry of the conjugate of a complex number. So recall that if Z is equal to A plus BI, its conjugate is A minus BI. Plotting this in the complex plane, we have the point A, B here, which corresponds to Z, and we have the point A comma negative B here, which represents Z conjugate. So this means that Z and Z conjugate are just reflections of each other over the real axis. So now we do the following example from the AMC 12. So the problem is, how many non-zero complex numbers Z have the property that 0, Z, and Z cubed, when represented by points in the complex plane, are the three distinct vertices of an equilateral triangle? So to attack this problem, we first draw a diagram. So our vertices are 0, Z cubed, and Z. Now, so we see that for this triangle to be equilateral, we must have that all the lengths must have the same length, and the angle between them must be 60 degrees, or pi over 3. So the first condition implies that the magnitude of Z is equal to the magnitude of Z cubed. But the magnitude of Z cubed is just equal to the magnitude of Z the whole cubed by de Moivre's theorem. So this implies that the magnitude of Z is equal to 1, or Z lies on the unit circle. So now, since the angle between adjacent sides of an equilateral triangle must be 60, we must have that Z cubed is just a 60-degree rotation of Z. So this means, by our previous discussion of rotations, that the argument of Z cubed over Z must be plus or minus 60 degrees, so, or pi over 3, and then plus 2 pi k, so adding on any multiple of 2 pi. So we can see that the left hand side is equal to the argument of Z squared, which is just equal to 2 times the argument of Z by de Moivre's theorem. So we have that the argument of Z is equal to pi over 3 plus 2 pi k over 2. Now we can test different values of k and see what arguments they produce. If we set k is equal to 0, we get two solutions. Z is equal to cis pi over 6 and cis 11 pi over 6. Similarly, if we set z is equal, or k is equal to 1, we get the solution z is equal to cis 7 pi over 6 and cis 5 pi over 6. So, and we can see that these are the only solutions, since if k is at least 2, then our argument will be greater than 2 pi. Therefore, we have 4 solutions. In summary, thinking of complex numbers in a geometrical way by using the complex plane and other techniques is a quite powerful tool to solve complex number problems.